Good, so we're in our last case. We have one real eigenvalue. Um, well, actually we have a double. So third case, we have, well, we'll just say a double eigenvalue. So we're going to work with the 2 by 2 case, and then only one eigenvector. And that means my matrix A is defective. Okay, and so given y prime is equal to a times y, with y of 0 being equal to y sub 0, the solution with eval lambda. So lambda is a double root, right? So you could say lambda lambda if you wanted to. We'll just say lambda and v. And then our solution is written in kind of an interesting way. It's going to be e to the lambda t times y0 plus t times w, where w is actually called a generalized eigenvector. This is kind of a weird way to do this, but it works pretty slick. We have to define our w now, and w satisfies a minus lambda I times y0 equals w. Okay, now notice in this expression here, a is known, lambda is known, y sub 0 is known. Therefore, w is a constant vector in this expression, right? And so you don't have to compute anything else. This is a constant vector right here. This defines your w. Good. So let's try an example. By the way, this is the results of this are going to be typed up and placed on the website. So example, y prime is equal to 4 minus 2, 8 minus 4. Maybe I shouldn't do this. Well, I like this one. It's kind of fun. The trace in this case is 0. Determinant is 0. So therefore lambda squared minus the trace of a times lambda plus the determinant of a equals 0 is our characteristic polynomial, or lambda squared equals 0. So therefore lambda equals 0 and 0. And so notice, by the way, that we don't have to solve for the eigenvector in this case. We're taking 4 minus 0 times our x0, y0, well, our y0, somewhere here. Maybe I should put it here. Let y0 be equal to, let's call it u0, v0 maybe. Hopefully that won't be too distracting. I'm just making that a generic number here because I didn't give you a specific y0. So this would be u0 minus 2 v0 equals w1, and then 8 u0 minus plus minus 4 minus 0 v0 equals w2, right? And so you have 4u0 minus 2v0, or 8u0 minus 4v0. That's our w1 and w2. Oops. Very good. Therefore, solution is e to the 0t in this case times u0 v0 plus t times, and then we'll just plug in our w, 4u0 minus 2v0 and 8u0 minus v0. Good. And so this is just a constant here, right? And you'll notice, by the way, that there are no arbitrary coefficients in this equation. That is the particular solution given an x0, y0. Excellent. All right. So the homework for this section is just going to be a few eigenvector eigenvalue computations. I'm leaving it a little bit short, so you'll have time to do some of the group work, which will be a little bit of work using Octave Online. So I hope you have some time to spend on that, and I'll see you later.